Okay, so I'm going to look at problem 4 in this video. So the first part of problem 4, we have this function d of t equals t minus t squared, and this is the distance of some car from its home after t hours. So the first thing we're asked is, at what time does the car return home? So let's plot a graph of d of t and see if we can figure this out. So d of t, we can factor this as t times 1 minus t. So we see that this is equal to 0 at t equals 0 and at t equals 1. So it ends up being a parabola, which looks something like this. And so this tells us that when t is equal to 1, d of t is equal to 0. D of t is this car's distance from home, so therefore that's when it returns. So the car returns home when d of t equals 0, which implies t is equal to 1. And so after t equals 1, the distance from home becomes negative, but of course distance cannot be a negative number, so that doesn't really make much sense. So therefore it makes more sense to say that we just want to limit the domain of our function to only this region. So since d of t is less than 0 for t greater than 1, the formula does not make sense as distance cannot be negative. And so therefore we limit the domain of d of t to the interval 0 up to 1. Okay, so that's part A. Next, we're asked to find the car's average velocity on this trip. So I've been noting average velocity by v bar. And so on the interval from 0 to 1, we see that the average velocity by definition is d of 1 minus d of 0 over 1 minus 0. But if we look at our graph here, d of 1 and d of 0 are both 0. So this is actually 0 over 1, which is equal to 0. And we should include our units on this. So the distance was measured in miles, and the time was measured in hours, so it's 0 miles per hour. And this is the average velocity. Of course, the car was moving inside this interval, but for the full duration of the trip, since it ended up back where it started, the average velocity is 0. So then in part C, we're asked to find some average velocities on some other intervals. So I'll do just one example, and then the rest are all very similar. So let's say for 0, 0.5, we have that v bar equals d of 0.5 minus d of 0 divided by 0.5 minus 0. Then if we plug 0.5 into our formula, we'll get 0.5 minus 0.5 squared. D of 0 is just 0. And we divide by 0.5. And if you simplify this a little bit, it works out to be 0.5. And so similarly, on the interval from 0 to 0.1, we'll get that v bar is equal to 0.9. On 0 to 0.01, it turns out v bar is equal to 0.99. And on 0 to 0.001, v bar is equal to 0.999. So in part D, we're asked how fast is the car moving at the start of the trip. Well, that is essentially d prime of 0. Right, it's the instantaneous velocity of the car at the beginning of the trip, so at time t equals 0. Based on our calculations in part C, we've been estimating the value of that derivative, and we see that it keeps getting closer and closer to 1. So, based on part C, it looks like d prime of 0 is equal to 1. But we can verify this if we use the definition of derivative at a point. So d prime of 0 is equal to the limit as h goes to 0, d of 0 plus h minus d of 0, all divided by h. If we plug in h to d, we'll get h minus h squared, and then d of 0 is 0, divided by h. We can cancel an h from everything, and we'll get limit as h goes to 0, 1 minus h, which indeed does give us 1. And again, it's worth keeping in mind that the units are miles per hour. And I suppose I forgot, but it would also be good to include this on all of our average velocities.